This is the video lesson for Introduction to Universal Gravitation. The learning target for this lesson is, I am learning to describe the gravitational interaction between two objects or systems with mass. The success criteria for this lesson are, I can understand Newton's law of universal gravitation describes the gravitational force between two objects or systems. I can understand a field models the effects of a non-contact force exerted on an object at various positions in space. So up until this time, we've always talked about contact forces. So when two objects interact with each other, they're touching each other and they exert a force on each other. So gravitational force is a non-contact force, meaning that the objects are exerting a force on each other without coming into contact with each other. And I can understand the gravitational force can be considered constant at all points between the initial and final position of an object's motion if the gravitational force has negligible change between those positions. So imagine we're talking about the top of a building and the floor, the ground floor of the building. So if the gravitational force has negligible change between those positions, so the gravitational force is basically the same at the top of the building and the ground floor of the building, and we have an object that's moving from the top floor of the building to the ground floor of the building, we can say that the gravitational force is the same from the top floor to the ground floor. So let's talk for a minute about projectile motion and what it says about the force of gravity. So here we can imagine we have a little ladybug flying through the air as a projectile. So the ladybug is not using its wings, it's been launched as a projectile and it's flying through the air along this trajectory. So the gray line is the trajectory that the ladybug is taking, and the red lines, these are gravitational field lines. So notice that they are uniform and they're pointing down towards the surface of the earth. They're all the same distance apart and they are all the same length, which means that it's a uniform strength of gravity. Okay, so in projectile motion, we assumed that projectiles traveled a relatively short distance and stayed at low altitudes. So this allowed us to make two simplifying assumptions. So one assumption is that the earth is flat, which we know is not true, and the second is that the gravitational field, which we call G, is constant. So neither of these assumptions that we were making are true. So Earth's mass creates a gravitational field, which again we assumed to be constant. So neither of these two things are true, but we use these assumptions when we were talking about projectile motion. So in reality, the Earth pulls inward from all directions. As your radius increases, the gravitational field lines spread out and they get weaker. So that gravity gets weaker with radius squared. So our gravitational field gets weaker with 1 over the radius squared. So here we can see in this diagram, we've got a body here, some circular body that generates gravity. We could think of this as the Earth. And then we've got our field lines, our gravitational field lines. So you can think of these as being like magnetic field lines. You think about a magnet, you have the North Pole and the South Pole, and we have these magnetic field lines that go from one pole to the next. Right? So these are gravitational field lines, and you can see that as they spread out, the gravity is stronger here than it is out here. And the further you get away from the surface of the planet or the surface of whatever is creating the gravity, the gravitational field is weaker as it goes out. And it's weaker by 1 over the radius squared. And the radius that we're talking about is from the center of the object out to wherever we're measuring the gravitational field. So from the center here out to here, where we would measure the gravitational field, that's the radius that we're talking about. Okay, so here's a diagram of a massive object that's creating a gravitational field. So the blue outline here, this is the large body that's creating a gravitational field. So this body has mass m, and this portion of this black line is our radius r. This portion of this black line can be considered the height. So we're going from the surface of let's say this is a planet, let's say this is Earth. So we're going from the surface of Earth out to a particular height away from the surface. So this whole distance here would be considered r. So we can come down here and say that r is equal to capital R plus h. So this r here is considered capital R plus h. So we talked for a minute ago about how the gravitational field gets weaker as the distance increases. So we can say that gravitational field G is proportional to 1 over the radius squared. And we can say that the gravitational field is equal to G is equal to big G m, so that's the mass of the planet or the body, over r squared. Okay, so here's an explanation of some of our variables here. So we have G, the gravitational field. So this is what we've been working with all year, or the gravitational acceleration. So the units for this are meters per second squared, or newtons per kilogram, also works. Big G, this is the universal gravitational constant. This is a value that's equal to 6.67 times 10 to the minus 11. This is newtons times meters squared per kilograms squared. This is universal. So this value for G is true all over the entire universe. So no matter where you measure this value G, you will find this value to be true no matter where you are. And this value is very, very tiny. This is a very small number. This makes gravity a very small force. Gravity is the smallest of the four fundamental forces that exist in our universe. You'll notice that this is 10 to the minus 11. So if you move this decimal place over 11 places to the left, you'll have the size of this number. So this is 10 zeros in front of this 6. That's how small this number is. Capital M, big M, is the mass of the object making the gravitational field, and the units for that are in kilograms. And then R is the distance to the center of the mass, and that is in meters. So again, little r is the distance from your whatever body we're talking about here. Say it's a satellite, say it's a moon, say it's a person orbiting the Earth, whatever. This body from here to the center of the object's mass, to the large mass, that is r. And this force here, or this acceleration, is g. Okay, we've looked at the acceleration due to gravity, the gravitational field. Now let's look at the force of gravity. So we know the force of gravity as being m times g. Well, let's build onto that a little bit further. So we know from the previous slide that the gravitational field, G, is equal to big G m over r squared. So now when you multiply G times m, you end up with the gravitational force is equal to big G times big M times little m. This little m is the mass of you're attracted to the Earth gravitationally, or it could be the mass of a satellite, it could be the mass of a moon, it could be the mass of any other object that's attracted to the larger of the two objects, divided by the radius squared. So notice here that F sub g is directly proportional to the large mass. It's directly proportional to the little mass. And it's inversely proportional to 1 over the radius squared. And again, little m is the mass of the satellite or the second object, whatever that is, and r is the distance between the centers of mass of each object. So that's important. We're not talking about the distance from the surface of the planet out to where the object is orbiting. We're talking about the center of mass out to the center of mass of the second object. So force of gravity is felt between any two objects. So me standing at the front of the classroom and you sitting in your chair at the other end of the classroom, we are exerting gravitational force between each other. So I could be the big M and you could be the little m, and the distance between our centers of mass, which is really just our middle somewhere, will give us the force of gravity between us, multiplied by the universal gravitational constant g. Or we could figure out the force of gravity between the sun, which would be the big circle here, and the earth, which would be the little circle here. So the big M would be the mass of the sun, little m would be the mass of the earth. The distance, r squared, would be the distance between the center of mass of the sun and the center of mass of the earth, times big G, multiply those together, and you would get the force of gravity between the earth and the sun. All right, let's talk about density. So here we have an object. Let's say it's a planet. The planet has mass m, it has radius capital R, and it has a certain amount of density. So the equation for density is rho. That's what this is. It's a Greek letter. It's spelled RHO, pronounced rho. So rho is equal to the mass of the object divided by its volume. So we have rho is equal to density, kilograms per meters cubed, and volume is V, which is meters cubed. So the volume of a sphere is 3/4, actually that should be 4/3, sorry, that should be 4/3, that's a typo, 4/3 pi r cubed. So that's the volume of a sphere. So if we wanted to solve for mass, we end up with rho times V. So that's density times the volume. And if we're talking about the volume of a sphere, we have rho times 4/3 pi r cubed. So notice that mass is proportional to the density, and it's proportional to the radius cubed of the object. So as rho increases, so as the density increases, the mass increases. And as the radius of the object increases, so does the mass. So a larger object has greater mass, and the more dense the object is, the greater the mass it has. And as we remember from previous slide, if we look at the force of gravity, Fg is equal to big G m over r squared. So the force of gravity is directly related to the mass of the objects that are exerting gravity on each other. So the mass of any object determines in part how much gravity it's exerting on another object. So the mass of the object is very important in terms of how much gravity it's exerting. Okay, so what have we learned in this video? We learned about the law of universal gravitation. we learned that objects exert gravity on each other proportional to their masses and inversely proportional to the square of the distance between them. We learned that gravity is a field. So gravity is a field that gets stronger the closer you get to the body exerting the gravitational field, and it gets weaker the further away you are from the body that is exerting the field. And that's true as the distance is squared. So it's an inverse square law. And finally, we learned that gravity can be assumed to be constant in certain circumstances. So the gravity field can be assumed to be constant close to Earth over short distances. So if you're close to the Earth, close to the surface of the Earth, and over short distances, we can assume that the gravitational field is constant. All right, thanks everybody.